adding rational expressions with different denominators. So we're going to look at this example. 7x over 2x minus x minus 2 over 20x plus 16. It's up to you guys. Yeah. I'll solve it the same way I did yesterday, or I started to yesterday, and then at the end, I'll see if you can tell me what the shortcut would have been. Okay, so the issue here is that we do not have the same denominators, right? So I have to figure out what are the factors in each denominator, right? Just like if we were adding a fraction like 2/6 plus 1/4, I wouldn't necessarily just multiply this times 4 over 4 and this times 6 over 6, because there's a smaller least common denominator, which is
12. So you can
12.
multiply the first one by 2 and the second one by 3.
So we could do 2 over 2 and 3 over 3. Because they already have a 2 in common, right? That's because 6 and 4 both have a factor that's 2. So if we find the factors that we have in common between the denominators, it's going to simplify this process. Now, in the first one, it's really already factored. 2 times x, those are the two factors of this denominator, 2 and x. In the second one, it looks factored. 20x plus 16 looks like a factor, but we could pull out a greatest common factor. So the first problem I'll leave the same, and then this one, I'm going to pull out a 4. And if I realize that 4 is 2 times 2, I can see that, oops, I did not do that right. I can see that I already have a 2 here. So to make it into a 4, I just multiply this times 2. Okay? So what are my factors? I'm going to circle them. In this one, my factors are 2 and x. In this one, my factors are 4 and 5x plus 4. Yeah?
So in the first fraction, to get it to equal like 4, you have to multiply it by 2. And you also have to have the 5x plus 4, so you multiply by 2, parentheses, 5x plus 4, close parentheses. And then on the other one, all you're missing is the x.
Right, so I just multiply this one times x. So now in both denominators, I will have 4, I will have x, and I will have 5x plus 4. So I'll have the exact same denominator, which is what I need. And my numerators will be rather complicated. The first one, I multiply this 7x times the 2 to get 14x. So that's just associative property, right? Associating this with this, or commutative property, over what I like to do if I know that my denominator is the same is I might just write like a line here, right? Because it can get kind of, you'll see the next steps will get kind of long if we write the denominator every single time. For now, I am going to write the denominator, 4x times 5x plus 4, minus, over here we have x times x minus 2 over 4x 5x plus 4. So again, I'm arranging my factors like I'm moving the x in front of the parentheses. That's just the commutative property of multiplication, right? I can always move things around if they're multiplied.
Oh, okay, yeah.
Yeah, I just moved the x in between these.
Couldn't you just do x squared minus 2x?
Okay, yeah, so now the next step is to expand our numerators. Okay, so what I'm going to do is use the distributive property. Sometimes you might have to use FOIL to do this, which is really actually the distributive property too, but you have to expand your numerator. So in the first one, I've got 14x times 5x. 14 times 5, I think, is 70.
Yeah, it's 70x plus 56x.
Okay, so we also have x times x, so it's
X
70x
squared, sorry.
squared. And then 14 times 4, you said 56?
Yeah.
56x.
Minus. And then you just put the
And this is where I would probably just not write a denominator. Okay, I know it's the same denominator. I'm not worried about rewriting it every time. Minus, and then the other one is
x squared minus 2x.
squared minus 2x. Denominator. Now, since it's a subtraction problem, I would use this little trick of saying, okay, I'm going to add a negative x squared and a positive 2x. So I distribute that subtraction through this numerator. Okay, now I'm going to kind of line up my numerators. So I've got 70x squared minus x squared, that's 69x squared. I've got 56x plus 2x, that's 58x, over
4x
4x. Okay. And now that I've expanded everything, now I have to factor everything again. Right? It seems like we're going back and forth, but I've combined all my like terms. So now I'm going to look at the numerator and say, can I factor anything there? You guys see anything that could be? We could take out an x. So I've got x times 69x plus 58 over 4x times 5x plus 4. Yeah, x is a factor of the top and it's a factor of the bottom. So I can cross that out. So we end up with 69x plus 58. Parentheses can kind of disappear over 4 times 5x plus. Okay, does anyone see the shortcut on this? There is a shortcut. Just on this particular problem. It's in the very first step.
You just cancel the x's.
Yeah. You could have canceled the x right here.
You just put an
X over x. I just put an x over x. Cancel. I could have canceled them right here, and then I wouldn't have had to multiply this fraction times x over x. Now, this is a little tricky because sometimes we don't actually want to cancel. Right? Like, technically right here, I could cancel a 2, but then I wouldn't have the same denominators. So we only want to cancel if it's going to make getting the same denominators easier or just the same. So you really have to look at the problem before you cancel in the early stage. At the end, you want to cancel everything you can, right? But over here, like, I just multiplied this times 2, so I don't want to then cancel the 2, because then I won't have the same denominators. All right, I want to outline the steps of what we just did. So step 1, right? We identified all the factors in our denominators. And I circled them, right? So I said, I know I have a 2, I know I have an x, I know I have a 4, I know I have a 5x plus 4. Step 2, I multiplied each fraction by the missing factors. So Well, I multiply this one times 2 and 5x plus 4, because they were missing from this denominator. I multiply this one times x, because that was missing from this denominator. So the goal here is same denominator. That's my goal. Okay, what did I do next? Step 3.
Add or subtract the numerator.
Yeah, so step 3, even before I added or subtracted the numerator, I expanded the numerators, right? I kind of unfactored them. Step 3, expand your numerators. And the whole reason we do that is so that we can combine like terms. So expand my numerators. Step 4, we add or subtract the numerator. And remember, in this problem, I used that little trick of it was minus, so I distributed that minus through the numerator. Instead of minus, I turned it to plus, minus, plus. It changed every sign in this, like from here over. Step 5, I combined like terms. And I sort of did step 4 and 5 at the same time, right? I never actually wrote 70x squared minus x squared plus 56x plus 2x. I didn't actually write that out in one numerator. I just said, oh, 70x squared minus x squared is 69x squared. 56x plus 2x is 58x. Step 6, factor the numerator and denominator so that we can, step 7, simplify or cancel. So here, the way that I factored it was I pulled out an x so that I could then cancel the x. If I had like 69x squared plus 126, if I had that, I would try to factor using Gary's terrific trick. Yeah, I mean that one would have been. I was so glad when I saw the 69x squared. I was so glad that we didn't have a constant there, right? Because that would have been really difficult to factor. So whatever ways you know of factoring, you have to factor. Factor the numerator and denominator, simplify. So I just want to point something out about this. This, starting either here or here, right, is all stuff that we've already done. We've already done simplifying rational expressions, which is the last 2 or 3 steps. Right? That's simplifying rational expressions. That's what we practiced all last week. The end of last week or the beginning of this week, we practiced from here down, right? Step 4 was when we had the same denominator to begin with, that was just adding rational expressions with the same denominator. So the only steps that are really new are the first 3. Identify the factors in your denominator, multiply each fraction by the missing factors, and then expand your numerators. And then once you've done that, you're really in the place of, oh, same denominators, I add them together. Now I have one fraction, I simplify. And you've practiced all of that stuff. So this is building upon itself, right? Each step of rational expressions builds upon the last steps. I mean, if you really think about it, this step, step 2, is multiplying rational expressions also, except we don't simplify them. Like when we practiced just multiplying, then we would simplify.
Why do rational expressions exist?
why do they exist?
Yeah, like what do they do? What are they used?
I don't know a ton of like really good examples of rational expressions. I've seen problems with rational expressions that are sort of statistics based. So like a really simple example. Can I erase all of this?
Yeah.
I guess I'll put this on the video too. It's a good question. This is not going to look as complex. The example that I'm going to give you, it's not going to look as complex as these, but a really simple example would be, say, like, there's a lot of statistics in sports. So say you're like a sports statistician, and you're analyzing this person's record. And let's just say, like, for the sake of simplicity, let's just say it's like a game of tennis or a tournament of tennis. And someone has played 12 games, right? And out of those 12, they won, let's say 7. Okay? Now we know they're going to play X more games. We don't actually know how many more games they're going to play. But they're going to play X more. So we could say the total number of games that they'll play will be X, 12 plus X. And the number of games that they would win would be 12.
You mean 7?
7 plus. Now, they're not probably going to win every other game they play. So it's probably something like X minus, and then we could just make another variable. But sometimes there's another way of doing that. Like we might say, we know that they win 50% of their games, so maybe it's X plus 0.5X. And then we could figure out their record at the end of the tournament based on a rational expression like that. So you can kind of create like this ratio that has the same variable on the top and the bottom. And then I've never actually seen an example of this, but I was looking up that very question because I knew you were going to ask it. It's not like I told her to ask it or anything ahead of time, right? No.
We just like the question that.
No, you always ask that question. But I was looking it up and I was reading that like in computer programming or computer science, rational expressions can come up as well. I don't know exactly how they would, but someone was saying, in a computer program it would be important to simplify your rational expressions. And I don't know exactly what they meant by that. But it's that analogy of like, what you're doing is taking something really complicated and making it simpler.
By doing a lot of really complicated things.
By doing a lot of really complicated things.
Yay!
It's sort of like it's like deriving the quadratic formula over and over and over and over.
Why?
Right? In a way.
Wait.
All right.